without further ado, I guess we'll kick it off in the actuation and control round with Martin Power from the University of Manchester. Come on up here. Off you go. Thank you so much.
No spoilers.
Oh, really? Interesting.
Yes. Okay, so hi, good morning, everyone. My name is Martin. I'm just finishing up my PhD in the University of Manchester in the Lee Group. And today I'm going to, I'll take that. Yeah, hi. So today I'm going to talk to you about one of the projects that I worked on, which is essentially demonstrating how you can perform work in the physical sense with a molecular motor, a small molecule molecular motor, by winding up polymer chains in a gel network. So in the Lee Group, our inspiration is the biomolecular motors that we find in nature. So a lot of these operate in a rotary fashion. There's two here. On the top is the bacterial flagellar motor, which is used by bacteria to kind of power their motion. On the bottom, you have ATP synthase. And in the past couple of years in the Lee Group, we've made a number of different artificial molecular motors from organic chemistry building blocks. And we can create kind of nanoscale motion, such as this example here, where you move a crown ether macrocycle along a larger ring. And we kind of wanted to explore in a bit more detail how these can kind of perform work and do more useful tasks. And so today's session is about control and actuation, and it's an ongoing topic on how we can link nanoscale changes, such as the things done by molecular motors, to macroscopic material changes or material properties. And there's been a lot of nice work done on polymer actuators and actuation materials. So this is the example here where you apply a voltage and the polymer will shift its position. And these are very nice, but an issue with these is that they're usually switches. So they're not motors, they're not progressively doing work. Once you switch them and you switch them back, you undo all the work that you've done. And so we're looking at how we can use molecular machines, and particularly molecular motors, and interface these other components, and how we can do work in the physical sense with these systems. And our collaborators on this project in Strasbourg in the Giuseppone lab have done this with light field motors. And I'm going to tell you today about how, in collaboration with the Lee Group and their lab, we developed chemically fueled motors for this purpose. So this is our molecular motor. It's very small. It's just a biaral system. It's 26 atoms. And you see in black on the bottom is the stator, and the rotor is on top in blue and red. Because it's a short talk, I can't go through the whole mechanism, but essentially this converts the chemical energy of this fuel to waste process. So you see this is the carbodiamide, which is the energy source, much like ATP would be the energy source in a biomolecular motor. And this is converted to this urea product, and that releases energy which can be coupled with the mechanical cycle of the motor. And essentially, if you start from this point here, the motor will react with the fuel and also this hydrolysis promoter, and you'll go through this continuous cycle where the rotor will continuously rotate on top as long as your fuel is present. So if you want to learn more about the mechanism, just ask me later and I can go through it with you. So this is the motor. It's 26 atoms and it's chemically fueled. As long as you continuously provide it with the fuel source, in this case the carbodiamide, the motor will continuously rotate. And it's analogous to a lot of the kind of biological rotary motors that we see in nature. It makes a mistake every 3 or 4 turns. It's not perfect by any means, but biology's had a 4 billion year head start on us, so hopefully we can catch up with them at some point. So now I'm going to get to the project that I actually worked on, which is integrating this molecular motor into a polymer gel network. And the reason we want to do this, there's a few reasons. First of all, we want to actually demonstrate that the motor is rotating. It's very difficult. It's something I've discussed with some people this weekend. It's very difficult to prove exactly what's happening on the nanoscale when you're trying to make these molecular motors, because they're so small. You have to use a lot of different experiments, a lot of different techniques to prove this. And we wanted a kind of very visual, clear demonstration that the motor is rotating. We also wanted to prove that the chemically fueled motor can perform work in the physical sense. It's all well and good to just have them spin around, but eventually you want them coupled to tasks. So by integrating them with the polymer network, we can actually cause the motor to rotate, and this will cause the polymer chains to entangle themselves and causes a macroscopic change in the system. Also, one interesting thing about this motor system that's not something you can do with the light field motors is that you can use different chirality fuels and you can spin the motors in 2 directions. So if you use one enantiomer of the carbodiamide, the motor will spin clockwise, and the other enantiomer will spin anti-clockwise. So it's a reversible system, and you want to explore that in detail a bit too. So now I'm going to get to the nuts and bolts of the project. So this is the motor molecule we made. It's a 16-step synthesis, so it's quite lengthy. I wanted to point out Peng Lai, who's the first author on this paper, who did some incredible work actually making this motor molecule. It was really quite a long task, and this was the real bottleneck of the project. But once we had made this, you can see it's the exact same motor that we're working with, but there's 4 kind of alkyne chains attached to it, and that allows us to functionalize the motor for the task we want to do. So we then use a click reaction. We click these azide functionalized peg chains onto the motor, and then you form this polymer gel network that's cross-linked by the molecular motor. And then we move on to the operation. So when we add our energy source, which is the carbodiamide fuel, the motor will rotate, and this will cause the polymer chains to entangle themselves up. You'll continuously rotate, the polymer chains will become more tangled, and then you see the gel actually contracting on the macroscopic scale. So this is a GIF here. Yeah, there you go. So you see when we add the fuel, the gel slowly starts contracting and shrinking. And what's happening here is the motor is spinning, polymer chains are tangling, and the gel contracts. So as I mentioned, yeah, we can plot this with imaging software, and you can see kind of the progress. At the start, it's very fast, but eventually you have this back pressure because the polymer gels become entangled, and you have a back pressure, and the motor can no longer work. And this is analogous to a stall force, which you see in biomolecular proteins. As I mentioned, this system is reversible. So what we can do is we can add 1 enantiomer of the fuel, and the motor will spin, tangle up the polymer chains, and the gel will contract. We'll go from this state here to this state here with the gel contracted. You can then wash out all the fuel and then add the other enantiomer, and the motor will start spinning in the reverse direction. The polymer chains will untangle themselves and then start tangling up again in the other direction, and the gel will contract. So you get a kind of in and out process. I'll just play the video now. Yeah, so when we add the other fuel, the gel expands as the motors are going in the reverse direction, and then slowly it'll start recontracting again over a number of days. The video is quite long, we won't go through all of it. But again, we can plot this using the imaging software. You can see this is the first contraction on the left, and then we wash out the reagents, add the other enantiomer of the fuel, expands, and then recontracts. So we did some kind of material characterization. I won't go through this in detail, but notably from AFM images, you see that these pores form in the contracted gel. And then when you look at the re-expanded gel, you more or less regain the original structure, showing that the material is reversible. And yeah, so that's the project. So we kind of demonstrated that by cross-linking polymer gels with molecular motors, you can undergo a powered contraction. So this is the first example of a catalysis-driven molecular motor performing work on the macroscopic scale, at least a synthetic one, to be specific. A synthetic organic motor that does basically what motor proteins do. We've demonstrated that the molecular motor can generate force without a power stroke. Power stroke is a part of the information ratchet mechanism that this motor goes through. And this is quite a debate in some aspects of the biophysics community. So we hope that this project can shed some light on that. And future work with this system will look at integrating these motors with, for example, biological systems, or further investigating the mechanism of force generation so we can kind of understand more about how molecular motors can perform useful tasks. So yeah, just wanted to thank, it's not working now. Yeah, thank all these people, my collaborators, and also the Foresight Institute and everyone for putting this nice workshop together. So thanks for your attention.
Questions, comments? Ted, you already have one.
I think this is really cool. When you mentioned the motor sometimes makes a mistake, I mean, what is the nature of the mistake? Does it go the wrong way, or does it stop moving, or what kinds of mistakes?
So it would take a back step. So you have, it's all dependent on the kinetic asymmetry between the forward steps and the backward steps. And for example, a biomolecular motor, it's perfectly tuned, so it never makes a backward step. But with our motor, occasionally it'll move backwards instead of going forwards. About 3 or 4 turns, yeah. Yes?
Can you replace the parole with, if I remember right, with proline?
Yeah, we've tried doing that. We tried lots of different variations of the rotor. Unfortunately, we don't have one that works better than this yet. But people are definitely looking at doing different things. And for example, with proline, then you've got a chiral unit on the top. So in this case, the motor will in fact have a power stroke as part of its mechanism. But unfortunately, we haven't got it to work better than the original motor yet.